Okay, let's talk about this problem involving a linear molecule. Here's the question we are tackling. We have a linear molecule modeled as two atoms, both with equal mass, which we'll call M. They are located at positions x1 and x2 along a line. These atoms are connected by a spring with a string constant K. Now the molecule isn't just connected by a spring, it's also moving within an additional external potential field. This external potential V depends on both x1 and x2. By V equals 1/2 m omega 0 squared times the quantity x1 squared plus x2 squared. The molecule is restricted to move only in one dimension. We are told that one of the molecule's vibrational frequencies is omega 0 and we need to find the other frequency. We've got 4 options here for the other frequency. Right. Let's set up the problem. Our system consists of those two atoms, each with mass m at positions x1 and x2. They are connected by a spring with stiffness, K. We also have that external potential we just mentioned, V sub E, which is 1/2 m omega 0 squared times x1 squared plus x2 squared. And importantly, all this motion is happening just in one dimension. The first step in analyzing such a system using analytical mechanics is to define the kinetic energy and the potential energy. The kinetic energy, which we call T for the system of two particles, is the sum of their individual kinetic energies. So T equals 1/2 men times x1 dot squared plus 1/2 men times x2 dot squared. Remember, x1 dot and x2 dot are the velocities of the atoms. Now the total potential energy V is the combination of the potential energy. V is the combination of the potential energy. V is the combination quaterniology. The energy from that external potential. The spring potential energy V sub S is the standard formula 1/2 K times the difference in position squared. So that's 1/2 K times the quantity x2 minus x1 squared. The external potential energy V sub E is given to us as 1/2 m omega 0 squared times the quantity x1 squared plus x2 squared. So the total potential energy V is the sum of these two. V equals 1/2 K times x2 squared. So the total potential energy V is the sum of these two equals 1/2 m omega 0 squared times x1 squared plus x2 squared. Next, we formulate the equations of motion for the system. A really powerful way to do this is using the Lagrangian formalism. The Lagrangian L is defined as the kinetic energy minus the potential energy. Plugging in what we just found, L equals 1/2 mx1 dot squared plus 1/2 mx2 dot squared minus 1/2 K times x2 minus x1 squared minus 1/2 m omega 0 squared times x1 squared plus x2 squared. To get the equations of motion, we use the x squared times x1 squared equations. For each coordinate xi, where I is 1 or 2, the equation is the time derivative of the partial derivative of L with respect to xi dot minus the partial derivative of L with respect to xi, and all of that equals 0. Let's apply the Euler-Lagrange equation for each coordinate x1 and x2. First, for x1, we need the partial derivative of L with respect to x1 dot. Looking at the Lagrangian, the only term with x1 dot is the first one, so the partial derivative is simply mx1 dot. Next, we need the partial derivative of L with respect to x1. The x1 terms are in the spring potential. The x1 terms are in the spring potential and the external potential. Taking the derivative, we get K times the quantity. One from the chain rule and then from the external potential, negative 1/2 m omega 0 squared times 2x1, which simplifies to negative m omega 0 squared x1. So the partial is K times x1 minus x2 minus m omega 0 squared x1. Let's check that derivative carefully. Yes, taking the derivative of minus 1/2 kx2 minus x1 squared with respect to x1 gives kx1 omega 0 squared x1. 1/2 m omega 0 squared x1 squared plus x2 squared with respect to x1 is minus m omega 0 squared x1. So the partial derivative of L with respect to x1 is K times x2 minus x1 minus m omega 0 squared x1. Now plug these into the Euler-Lagrange equation for x1. The time derivative of mx1 dot, which is mx1 double dot minus the partial derivative with respect to x1. This gives us mx1 double dot minus the partial derivative with respect to x1. Omega 0 squared x1 equals 0. Rearranging this equation, we get mx1 double dot plus the quantity K plus m omega 0 squared times x1 minus x1 from the spring potential minus. Now let's call this equation 1. Now let's do the same for x2. The partial derivative of L with respect to x2 dot is mx2 dot. The partial derivative of L with respect to x2 is minus K times the quantity x2 minus x1 from the spring potential minus x1 from the string potential. Plugging these into the Euler-Lagrange equation for x2. The time derivative of mx2 dot, which is mx2 double dot, minus the partial derivative with respect to x2. This gives us mx2 double dot minus the quantity minus k times x2 minus x1 minus m omega 0 squared x2 equals 0. Rearranging this equation, we get mx2 double dot minus k times x1 plus the quantity k plus minus d rho squared times x1 plus the quantity k plus my omega 0 squared times x2. We now have a system of two coupled linear second-order differential equations. To find the natural frequencies or normal mode frequencies, we assume harmonic solutions. Let's assume that each position xj is some amplitude, aje multiplied by e to the power of I times omega t, where omega is the frequency we are looking for and I is the imaginary unit. If xj is aje to the I omega t, then the second time derivative xj double dot will be minus omega squared times aje to the I omega t, then the second time derivative xj double dot will be minus omega t. Substitute these assumed solutions into equation 1 and equation 2. The e to the I omega t term will cancel out from every term in both equations, leaving us with equations for the amplitudes a1 and a2. Substituting into equation 1 minus k a1 minus squared a1 plus the quantity k plus m omega 0 squared times a1 minus k a2 equals 0. We can rearrange this to group the terms with a1 the quantity k plus m omega 0 squared minus m omega 0 squared all times a1 minus k a1. 2 equals 0. Substituting into equation 2 m times minus omega squared a2 minus k a1 plus the quantity k plus m omega 0 squared times a2 equals 0. Rearranging this minus k a1 plus the quantity k plus m omega 0 squared all times a2 equals 0. We now have a system of two linear homogeneous algebraic equations for the amplitudes a1 and a2. We can write the system in matrix form. We'll have a 2 by 2 matrix multiplied by a column vector containing a1 and a2, and that equals a column vector of zeros. The matrix elements come directly from the coefficients of a1 and a2 in the equations we just derived. The top row is the coefficients from the first equation, Ck plus m omega 0 squared minus m omega squared, m plus m omega squared minus m omega squared and minus k. The bottom row is the coefficients from the second equation minus k and k plus m omega 0 squared minus m omega squared. So the matrix is k plus m omega 0 squared, m omega squared, dkk plus m omega 0 squared, m omega squared. This matrix multiplies the vector a1, a2 and the result is the vector 0, 0. For this system of homogeneous equations to have non-trivial solutions, meaning solutions other than a1 equals 0 and a1 equals zeros other than non-trivial solutions, meaning solutions other than a1 equals 0 squared, akkkkkkkkk plus m omega 0 squared, m omega 0 squared. Atoms not moving the determinant of the coefficient matrix must be 0. Let's calculate the determinant of that matrix. Let's make things a little simpler by defining a temporary variable. Let lambda be equal to k plus m omega 0 squared minus m omega squared. Then the matrix looks like lambda minus k lambda. The determinant equation is lambda times lambda minus the product of the off-diagonal terms, which is minus k times minus k. So the determinant equation is lambda squared minus k squared equals 0. This simplifies to lambda squared minus k squared equals 0. This simplifies to lambda squared k squared equals 0, which means lambda squared equals k squared. Taking the square root of both sides, lambda must be equal to plus or minus k. Now we have two cases for lambda which will give us our two normal mode frequencies. Case 1, lambda equals positive k. Remember, lambda is k plus m omega 0 squared minus m omega 0 squared. Taking the square root, find the finus m omega 0 squared equals k. Subtract k from both sides, m omega 0 squared minus m omega squared equals 0. This means m omega squared equals m omega 0 squared. Dividing by m, we get omega squared equals m omega 0 squared. Digging the square root, we find the first frequency omega 1 equals omega 0. What does this mode correspond to? If we plug lambda equals k back into the matrix equations for a1 and a2, we find that a1 equals a2. This means the two atoms move together in the same direction and with the same amplitude. This mode represents the motion of the center of mass of the molecule. Case 2, lambda equals negative k. Using our definition of lambda k plus m omega 0 squared minus m omega squared equals minus k. Let's rearrange this. Add k to both sides. 2k plus m omega 0 squared minus m omega squared equals 0. Or rearranging to solve for m omega squared equals m omega 0 squared plus 2k. Now divide by m omega squared equals omega 0 squared plus 2k. Now divide by m omega squared equals omega 0 squared plus 2k over m. Taking the square root of squared minus n squared minus n omega squared equals 0 of omega 0 squared plus 2k over m. What does this mode correspond to? If we plug lambda equals minus k back into the matrix equations, we find that A1 equals minus A2. This means the atoms move in opposite directions with the same amplitude, stretching and compressing the spring. This is the internal vibrational mode of the molecule, but influenced by that external potential. So we have found the two normal mode frequencies for this system. The first frequency, omega 1, is omega 0. The second frequency, omega 2, is the square root of omega 0 squared plus 2k over m. The problem statement tells us that one frequency of molecular vibration is omega 0. Therefore, the other frequency must be the second one we found, which is the square root of omega 0 squared plus 2k over m. Let's look back at the options given in the problem and see which one matches our result. The other frequency is the square root of omega 0 squared plus 2k over m. Option 1 is the square root of omega 0 squared minus k over m. That's not it. Option 2 is the square root of omega 0 squared plus k over m. Not quite. Option 3 is the square root of omega 0 squared plus 2k over m. Yes, this matches. Option 4 is the square root of omega 0 squared plus 2k over m. Yes, this matches. Option 4 is the square root of omega 0 squared minus k over m. Also not it. So the correct option is 3. The final answer is the square root of omega 0 squared plus 2k over m.